This is lecture 6, and the title is Earth's Atmosphere and Climate. This is a picture of the Earth, and you might imagine that the Earth has always looked like this, but we now believe that in fact at some point in Earth's past, in fact a couple of times in Earth's past, it actually looked like this, and that at some point in the past the Earth was a snowball. It was completely covered in glaciers with extremely thick ice covering most of the globe. So it went through a much colder period than we have right now. And this lecture is going to be about understanding the nature of our atmosphere, how the atmosphere plays a role in the temperature of the Earth, and also other things, the external forcings that might affect global climate on the Earth. And of course, that affects things like life. The kinds of life that can exist are going to be a little different with this kind of Earth than this kind of Earth. Now, one thing to keep in mind, yesterday was Earth Day, and everybody was all appreciating how awesome the Earth is, and this is another way of thinking about what could have been. Okay, we have basically 3 terrestrial planets in the solar system, planets that really aren't that much different than the Earth in terms of how massive they are, and actually, broadly speaking, their distance from the sun isn't that much different. But they're very, very different. Okay, so Venus, which is the second planet from the sun, very, very similar to the Earth, ends up having a temperature that is just crazy higher than the Earth, with typical temperatures of about 430 degrees Celsius or 800 degrees Fahrenheit on the surface of Venus. So it's a very, very hot place. And you might think initially that the reason why it's so hot is that it's closer to the sun, but it's not. That's only a tiny piece of the story. The reason why Venus is so hot has to do with its atmosphere. Then, of course, we have the Earth, which has an average temperature that's something like 60 degrees Fahrenheit. We have liquid water. It's reasonably comfortable for us all over the globe. And then, on the other extreme, we've got Mars. And Mars is a crazy cold place most of the time. It's basically a desert because there's almost no atmosphere. It's extremely dry. And its average temperature is something like minus 50 degrees Celsius or minus 60 degrees Fahrenheit. There are places on Mars where it gets a little bit warmer than that, but broadly speaking, it's a very cold place. And so then what we'd like to do is understand a bit about why that is. One of the really important aspects of Earth's atmosphere, okay, is that it's well, for many reasons, the Earth's atmosphere is important for sustaining life. However, the atmosphere we enjoy today is very different, actually, than the atmosphere we think existed on the early Earth. And so one of the questions we want to ask is, how did it get to be the way it is now? We will discuss this in a few different lectures because it turns out the contents of our atmosphere are very much driven by the fact that we have life. So the fact that there's photosynthesis on Earth generates the oxygen that we have in our atmosphere. And without that life, we would have an atmosphere that was basically devoid of oxygen. Now, let me just remind you that the atmosphere of the Earth, although it plays this really important role in setting the temperature of the surface of the Earth and the temperature of the oceans, is a teeny tiny thing. And it's sort of basically, if you took the Earth and shrunk it down to the size of an apple, it would basically be that apple skin. So that atmosphere that sort of protects us and keeps us warm is like the skin of an apple. So it's just this small little bit, but it's a very important thing. If you ask what it's made of, we've talked about this before, but it's mostly nitrogen and oxygen. It's about 21% oxygen. And then there's a sliver of argon, carbon dioxide, etc., which is about 1%. And then there's water vapor. And the content of water vapor in the atmosphere varies from something like 0% to a couple percent. And I'll return to that again. But the water vapor actually varies quite a bit within the atmosphere. Fundamentally, that's because water doesn't last that long. You put it in the atmosphere and it rains out. And it's not a really stable component of the atmosphere. It basically will stay in the atmosphere a couple days. Unlike these other gases, which can hang out in the atmosphere for a long time. Now, if you back up for a second and you look at the atmosphere of the Earth, if you look at the gases that make up the atmosphere of the Earth, they're sort of weird. If you remember, I told you before that the most common elements in the universe are hydrogen and helium. And we think that when the solar system formed, the cloud of stuff that it formed out of was mostly hydrogen and helium. In fact, mostly hydrogen, really. And if you look at the sun is also mostly hydrogen and helium. And if you look at big planets like Jupiter, they're mostly hydrogen and helium. And so you might ask yourself, why does our atmosphere not have any hydrogen and helium in it? This is an important question, because if our atmosphere was a mostly hydrogen atmosphere, it would not be very conducive to life. Okay? Hydrogen binds to everything. Okay? It's a very reactive kind of thing, and it would not be very good for freeing up the complex elements that we want to free up to enable life to happen. So why is the Earth not made of hydrogen and helium in terms of its atmosphere? Well, the first reason is this stuff floats away. Okay? If you had a bunch of helium here on Earth, it would float up. We know that, right? If you take a helium balloon and let it go, it floats. It escapes the Earth. Right? And it's light. It's one of the light elements. So it's so light, it floats. Yeah?
It actually escapes Earth?
It escapes Earth. Yep. If you take a bunch of helium and you let it go, it will escape the Earth. So keep in mind, by the way, that's why helium is kind of rare on the Earth. Okay? If you let some helium go, it goes away. Hydrogen also floats. Okay? Now, we don't put hydrogen in balloons for children because this kind of thing happens, right? Hydrogen is very volatile. It creates fires. It's flammable. It used to be that people tried to pump hydrogen in sturdy air balloons and fly them around the world, okay? But people figured out that probably wasn't such a good idea. And this is the famous Hindenburg disaster that happened in 1937. And this was kind of the last time that people were really trying to do airships out of helium. We don't do that anymore. But in principle, you could do that, right? You could, fill a balloon with hydrogen, it would float up. Right? But the point is, hydrogen floats, helium floats, that's why it's not on the Earth. Now you might want to ask, okay, I sort of get it. The Earth is not holding on to its hydrogen and helium. Let me add a little bit to the mix, and let's think a little bit about why this is. Okay? The atmosphere of the Earth has a temperature. Okay? Let's say it's something like 60 degrees Fahrenheit. So it has a temperature. What does a temperature mean? So thermodynamically, if you think about what temperature really is, you're describing the motions of molecules or atoms in some container. Okay? The room has this temperature. What does that mean? That means that the molecules that make up the air in this room are moving around with some speed. And if you cranks up the temperature in the room, what that means is that the motions are faster. There's more kinetic energy in the molecules that are moving in the room. That's what heat is. Heat is basically, that's what temperature is. Temperature is basically some way of describing how quickly moving, how much energy, how much kinetic energy on average the particles in some box or in some room are moving, or how much energy they have. Okay. So let me show this movie again. What's shown here is of what it would look like if you could actually watch molecules or atoms bouncing around in a box of a given temperature. Now, one of the things you're supposed to see in this movie is that the red things are moving more slowly than the blue things. This is supposed to represent, so the blue things are supposed to represent light molecules, and the red things are supposed to represent heavy molecules. Now, what happens when something has a characteristic temperature, that means the energy per particle is the same. They sort of have divided up the energy. But what's going on here is you can imagine these red things as being heavy objects, like say bowling balls, and the blue things as being light things like pool balls. Okay, and imagine you had pool balls and bowling balls bouncing around in a cage because they had some shared energy, right? Whenever the bowling ball gets hit by a pool ball, the pool ball will bounce off more quickly than the bowling ball. Right? Imagine that. Imagine you have a bowling ball, you throw a pool ball at it, it bounces off. The bowling ball will roll off more slowly than the pool ball. Right? That's because the bowling ball is heavier. It has more momentum. And in fact, when you average out the energy per systems, more massive things can be going more slowly and have the same energy as a low mass thing that's going quickly. That's kinetic energy. Okay? So if you have a system of particles, all with the same kinetic energy, on average, the more massive things will be moving more slowly than the light things. Does that make sense? Are there questions about this? Now, so low mass things are going to be moving fast, and high mass things are going to be moving slow. So if you have a bunch of different types of atoms in a box, and everything in that box has the same temperature, then the heavy things are going to be moving more slowly than the light things. Okay? Now, you can actually calculate exactly what that speed should be if you have the temperature. It turns out that the velocity of any given molecule of mass m, when it's sitting in a box of air that has some temperature T, is given by this equation. Okay? And so the velocity is equal to the square root of 3 times the temperature, and this is a constant that's called Boltzmann's constant, divided by the mass of the particular kind of atom or molecule you're talking about. So we know exactly what the relationship is between the velocity of a particle, the temperature of the temperature it has, and the mass that that particle has. The important thing is, as the mass goes up, the velocity goes up or down? Down. Good, down, right? So if this is in the denominator, if this number gets bigger, this number gets smaller. Yeah?
How did we come up with this number?
This equation?
Some guy just like guessed it?
No. So this, well, I mean, this is if you took physics 3, you would learn this. So this is sort of very, very basic physics. The way you basically calculate this, there's something called kinetic energy. And kinetic energy is basically the velocity, the mass of the thing, the little molecule, times the velocity squared, times a coefficient that turns out to be 1/2. And so the velocity of the kinetic energy of anything with moving speed v and velocity m, moving at speed v and mass m, goes like the mass times the velocity squared. When you talk about something having a temperature, that means things have equal partition of energy. So fundamentally, that's what temperature means. It means that every object has on average the same energy. So by associating the temperature of an object and then assuming that, by definition, if something has a temperature, that means all the particles in that conglomerate have the same average kinetic energy. You can work out what the speeds are. And so the point being is that the energy scales like the velocity squared times the mass. Okay? And so on average, the velocity squared times the mass is going to be the same between particles of different masses. So when one mass goes up, the velocity has to go down to keep that equal partition of energy the same. So that's where that comes from. The 3 comes about because there are 3 spatial dimensions, it turns out. And this Boltzmann constant, you can think of it as a fundamental constant of nature that relates the definition of temperature to the definition of energy. So it's the thing that connects energy and temperature. So all of this stuff was basically developed in the 18th and 19th centuries. Good question, though. Other questions? Yeah. So this is not a magical formula. This formula is based on sort of many, many years of study, but it's now considered sort of within the canon of basic physics. It's something that sort of is fundamental and sort of very well understood within sort of physics. And if you take a basic chemistry class, you probably, I would imagine, I don't teach those classes, but I would imagine you would also discuss this as well. Okay. So now you've got your molecule. It's moving around, and let's just assume it's moving straight up. What will happen? Okay, let's just pretend we're on an empty plane here. I take my molecule, I throw it up in the air. Okay, what keeps that molecule from escaping to outer space? Gravity, good. The same reason why a ball, if I throw it up, it doesn't escape to outer space. It comes back down because of gravity. Okay? Gravity is what goes up must come down, right? Unless it goes up really fast and then it doesn't come down. Okay? Unless it's moving faster than what's called the escape velocity. So when we launch rockets off the surface of the Earth, they don't come back down because we launch them so quickly that they overcome what's called the critical escape velocity of the Earth, and they never come back down again. Okay? So the basic idea is, it turns out that the escape velocity of the Earth is about 11 kilometers a second. If you launch something at a speed faster than 11 kilometers per second, it just keeps going and it won't come back. If it's more slowly than that, it might go up for a while, but it's eventually going to come back down. And when you throw a ball up, you never throw it faster than 11 kilometers a second, so it always comes back down. Okay. Now, it also turns out that you can calculate exactly what that escape velocity is if you know the mass of your planet and the radius of your planet. And this is another one of these things that derives from basically the laws that Newton presented when he first wrote down the theory of gravity, that there's the escape velocity of a planet of mass big M and radius big R is equal to the square root of 2 times g, which is another constant, doesn't matter, times the mass divided by R. The point of this is, we know the mass of the Earth, we know the radius of the Earth, we can calculate the escape speed of the Earth, and if you work all these numbers out, you get 11 kilometers a second. And you can imagine applying this equation to other planets. Okay? So let's imagine that you had a planet that was the same radius of the Earth, but it was much more massive than the Earth. Would the escape speed go up or down? Who thinks up? Who thinks down? That's good. Right, so it goes up. If the mass goes up, it's harder to escape the planet. So more massive planets have really strong gravitational fields, and it's harder to escape off of them. Okay? Or you could go to something like the moon, right? The moon is less massive than the Earth, so the escape velocity is lower, and it's easier to get off the moon than it is to get off the Earth. That's why astronauts can jump so high on the moon, right? Because there's less gravity, there's a less restoring force, and it's easier to do. All right? Where the hell am I going with this? So now I've taken this sort of side, I started talking about temperatures, and now I'm talking about velocities. What am I talking about? Why am I doing this? All of this stuff matters. Okay? Because if you've got a planet with a given temperature, okay, low mass molecules and atoms, for example, hydrogen and helium, will move faster, okay, than high mass molecules like nitrogen and oxygen. Okay? And so if you have light molecules, they'll be moving faster and they'll be easier to escape. Whereas the heavy molecules will be moving more slowly below the escape velocity of the planet, and they won't escape. Okay? So at the Earth's temperature, hydrogen and helium move faster than the Earth's escape velocity, and they therefore escape. That's why helium balloons float. Now, if you took some helium and cooled it down and made it very, very cold, it will get denser and move more slowly, and if you put it in a balloon, it would just drop until it warmed up again, and then it would float. Right? Because it would be moving more slowly if it's colder. So, the ability of a planet to retain an atmosphere of gases depend on the mass of those gases, the mass of the planet, and the temperature of the planet. Okay? The more massive planets have bigger escape speeds, and at higher temperatures, molecules move faster, but at a given temperature, bigger molecules move slower. So you have to know how massive your planet is, how hot your planet is, and you've got to know what kind of molecule you're talking about to know whether or not those molecules are going to escape. Does that make sense? So, then you can make a plot like this. And I'm going to show this plot a few times. It's a cool plot. So people like me get excited about plots. You may not get excited about plots, but I do, so you got to bear with me. Okay, so what are we plotting here? This here, on the y-axis here, is the escape velocity. Okay? Of any given molecule as a function of that molecule's temperature. So, here's hydrogen. I'm sorry, wait, sorry. That's not what I meant to say. This is labeled escape velocity, but that's not what I meant to plot. That's not what I meant to say. Let's back up. Here's the Earth. Let's start with this. Here's the Earth. Here's our Earth. We love it. This is a characteristic temperature of the Earth, okay? At some height above the atmosphere. Okay? It's sitting here at some temperature, and it has an escape velocity of something like, 10-ish, 11-ish kilometers a second. What's plotted here in these lines are the thermal speeds, how fast these different molecules are moving at given temperatures. Okay? So helium, because it's so light, is moving faster than all these other molecules at all temperatures, because it's light. But when it's really hot, it's moving even faster, and as it cools down, it moves more slowly. Okay? And that same trend is true no matter what molecule you're looking at. So here, for example, is carbon dioxide. Carbon dioxide is also faster when it's hotter, and it's colder when it's slower when it's cooler. But the absolute speed it's moving is much lower than that of helium because it's much heavier. It's a much more massive thing than helium. Right? So you can work this out for any kind of molecule you're worried about. So if you put Earth on here, you see, okay, well look, Earth, the escape speed of the Earth is above that, the typical thermal speeds of water vapor, oxygen, nitrogen, and carbon dioxide. So you might naively think that water vapor, oxygen, nitrogen, and carbon dioxide are going to stay on the Earth. However, the escape speeds of helium and hydrogen are above that speed. The thermal speeds of helium and hydrogen are higher than the escape speed of the Earth, and therefore they're going to escape the Earth. So broadly speaking, this is why the Earth has nitrogen and oxygen, but doesn't have hydrogen and helium in its atmosphere. But the cool thing about this plot is you can put other planets on here, because remember, other planets have different masses, and they also have different temperatures, because they have different distances from the sun, and because their atmospheres are different, that also affects their temperatures. So there's the Earth. The Earth loses hydrogen and helium, but retains water vapor, oxygen, nitrogen, and CO2. Well, let's put some others on here. Here's Jupiter, Saturn, Neptune, Uranus, okay? They have huge escape speeds because they're massive things. And they're cold because they're far out, away from the sun. So they're so cold and so massive that they can hold on to all of these different kinds of gases. And that's why their atmospheres are mostly hydrogen and helium for the most part. At least these things. Okay? So massive cool planets like Jupiter retain all kinds of molecules. They have mostly hydrogen and helium in their atmosphere, and it turns out hydrogen and helium atmospheres are very bad for complex chemistry. We'll talk about this later, but you don't expect a lot of easily creatable complex chemistry going on if you're just in a bath of hydrogen and helium. Helium is totally inert, so helium doesn't bind with things. So that's not a good thing for doing complex stuff with. And hydrogen just binds with everything. So it sort of shuts things down and traps molecules, binds them up. There's Mercury down here, right? So Mercury is a tiny hot planet. It basically loses everything and doesn't have any atmosphere at all. Mercury, that's what Mercury is. It's just a rock. There's very little atmosphere on Mercury. It's so hot and so low mass that it can't hold on to anything. These things are really interesting, Triton and Titan. They're moons, okay? And they are very low mass, but they're extremely cold. So they're so cold that they can actually hold on to stuff in their atmospheres. So they're really low mass things. They're basically as low mass as Mercury, but they're so cold that they actually can retain an atmosphere. And so distant things, even Pluto might have an atmosphere. So things that are really far away, even if they're very low mass, can hold onto an atmosphere because those atmospheres are cold and dense. They're not moving fast, so they're below the escape speed. So the cool thing about this is you can kind of in broad brush look at all the planets in the solar system and get a sense of why they have the atmospheres they do. And if you would have taken the Earth's mass and changed it a little bit, it would have changed the atmosphere of the Earth, and that would affect things fundamentally. Are there questions about this? So just in summary, there's so little hydrogen and helium in the Earth's atmosphere because the hydrogen and helium are small and light and they're moving fast. They're moving so fast, they're bigger than the Earth's escape speed, and they float away. We have a lot of nitrogen and oxygen in our atmosphere. This is allowed because oxygen and nitrogen are heavy enough molecules that they're moving more slowly than the escape speed of the Earth, and they stay bound to the Earth. Okay, now we've talked about why we have the atmosphere we do. Why do we care? What is important about our atmosphere? Who knows what's important about our atmosphere? Give me some reasons. Why are we happy we have an atmosphere? Yes?
Protects us from the sun's harmful rays.
Great. It protects us from the sun's harmful rays. So there's UV radiation coming in from the sun, UV radiation is bad, okay? It tends to be made of high energy photons and damages cells, can damage DNA, right? And our atmosphere protects us from that. In particular, it's the ozone in our atmosphere that's really good at protecting us from that UV. Ozone is oxygen, okay, O3, and that comes from life. And so there's really this interesting kind of symbiotic relationship between the life on Earth that produces the oxygen and how that oxygen provides a protective layer from UV radiation that allows more complex life like us to thrive on the surface. So that's one thing that the atmosphere does. What else does the atmosphere do? Yeah?
It allows for the existence of liquid water.
Very good. The atmosphere on the Earth, you've either read ahead or you're just, well, a knowledgeable person. Either way, it's awesome.
Mars doesn't have
Very good. Right, that's right. Yes. So as we're about to talk about, the Earth has an atmosphere, right? And the Earth's atmosphere gives us pressure. And the atmospheric pressure allows for the existence of liquid water. If we had very, very low atmospheric pressure, as you point out, like there is on Mars, we basically couldn't have liquid water on the surface of the Earth. And I'm going to talk about that in a bit. So just the mere existence of that atmosphere, providing us with that atmospheric pressure, allows for the existence of liquid water, which is really cool. Anything else the atmosphere does for us that anyone knows?
Lets planes fly.
Lets planes fly. That's very important for us these days. Without that, we couldn't have planes fly. It also lets us hear each other when we talk. You know, if there was no air in this room, we not only would be dead and have nothing to breathe, but we couldn't talk to each other, which is, what's the point of life anyway, right? So, yeah, so it does a lot of cool stuff for us. Two things I want to emphasize in this lecture, though, is that it allows liquid water in two ways, okay? The first way we've already discussed, which is a really cool reason because of this pressure thing, okay? It provides atmospheric pressure, and it also keeps the Earth warm. It's a blanket, okay? And this is the famous greenhouse effect that I'm going to talk quite a bit about in this lecture. Now, as we were just talking about, high air pressure is fundamentally necessary for liquid water to exist. Without high air pressure, you cannot have liquid water. There's a famous thing you might discuss, for example, if you take a chemistry class. There's something called the triple point of water, which goes something like this. Whether or not you can have water, and in what form H2O will exist in, depends on the temperature of that stuff, right? And we're pretty familiar with that. But it also depends on the pressure. So we're all familiar with life at 1 atmospheric pressure. That's just where we live. That's how we've sort of grown up. That's sort of reality to us. And we all know that if it's cold, right, if it's colder than 0 degrees Celsius, water turns to ice. If you take water and you make it that cold, it's ice. If you warm it up above 0 degrees Celsius, it melts. And if you keep warming it up past 100 degrees Celsius, it starts to boil. And it will turn into vapor. And so at fixed pressure, there's a phase of ice, and then you heat it up more, it's water, and then at some point, it becomes water vapor again. So that's at sea level. That's at 1 atmospheric pressure. Water boils at 100 degrees Celsius. But if you go 5.5 kilometers up on a mountain, your water boils at a lower temperature, right? And that's why if you cook your spaghetti at altitude, it takes longer to cook, because the water's not as hot while it's boiling. Okay, so the water then is only 180 degrees, or it's 82 degrees Celsius is when water boils at roughly half an atmospheric pressure. Similarly, it turns to ice at a slightly different temperature too. Okay, it's got to be actually a little bit warmer to turn to ice at that point. Now, as you keep cranking the pressure down, at some point, if the air pressure drops to 0.6%, okay, 0.006, it hits this magical point where it's ice, and then when it gets heated up just a little bit more, it doesn't turn to water anymore, it turns directly to vapor. It boils. It starts as ice, and then it just boils into vapor. There is no water phase. Okay? What are you familiar with that does this? There's another kind of thing that does this. Yeah, dry ice, good, right? So dry ice does this. If you've ever seen dry ice, it looks like ice and then it's smoking. Okay, it's boiling at room temperature, it just boils. So it's boiling directly from ice to vapor. So it just has a different triple point, and the triple point of dry ice is at 1 atmospheric pressure, you're in this regime. Okay? So what does this mean? If we lived on a planet like Mars, where the atmospheric pressure was so low, you could really not have stable liquid water. You just immediately turns to vapor or it's ice. There's nothing in between. And given how important water appears to be for life on Earth, this matters a lot. Okay? So I'll just show you. Mars is somewhere around right here. Okay? So it's certainly at a point where if there's any liquid water on Mars, it only exists at a very narrow range of temperatures. Okay? So, and it looks like Mars is very, very close to the triple point of water, and that's why there's really no flowing water on Mars now. Okay? We do think that there's ice on Mars. There's water ice on Mars, and there's probably water ice underneath the surface of Mars, as I'll discuss later, but there's not flowing water on Mars right now. And this is basically why it's kind of physically impossible for there to be a lot of flowing water on Mars. Okay. But there's another thing, right, that we care about liquid water. It's the temperature. And so we can ask ourselves, what is the temperature on Earth, and why does it have the temperature it has? All right? So I want to walk through this a little bit. The first thing I want to just mention to you is when you have something that's hot, okay, there's a pretty precise, we have this kind of qualitative understanding of what temperature is, like what it means when something's hot or cold. But it turns out that over the last couple hundred years, physicists have figured out a pretty precise understanding of temperature. And part of that bit about temperature has to do with how fast stuff is moving. We talked about the speeds of molecules. But another thing that's kind of amazing about temperature is if you take something and you heat it up to a given temperature, it will glow. It will always glow. Everything that has a temperature is glowing. Now you're a little bit familiar with this in the sense that if you've ever heated up a rock in a fire, or you have an iron on a stove that gets very hot, you'll see it glow red, or coals in a fire will glow red and sometimes even blue when they're very hot. That type of emission is called blackbody radiation. I won't teach you on that. I won't ask you about that name. But the amazing thing is anything that's hot glows, and the temperature of that thing tells you what color it's glowing in or what type of radiation it's glowing in. So we are glowing, okay? Things that are at roughly room temperature glow, but they emit light in a wavelength that you can't see. They emit light in the infrared, okay? And so what we feel is heat, right? If you're in a crowded elevator and you're around all these people, they are emitting infrared radiation that you feel is heat. So heat is infrared radiation, okay? The sun is also glowing, but the sun is much hotter. It's like 6,000 degrees, the surface of the sun, and that's why it shines, okay? The sun is so hot that it's shining, but its radiation is in the visible, not in the IR, and that's why the sun is shining. The point is that things emit light, emit electromagnetic radiation, but the wavelength of that electromagnetic radiation depends on the temperature of the thing that's emitting the light, okay? The sun, here's just an example. It's the relative power of the amount of energy coming out of the sun. The sun is glowing at wavelengths that correspond to visible light. If you were to look at the Earth is also glowing, but because it has a temperature of about 60 degrees Fahrenheit, it glows at wavelengths that are much longer than that in the infrared. But they're both glowing, okay? So if you look at somebody, right, the light you see from them is the reflected light from the sun or from the lights. That's what you see with your eye. But if you could see an infrared, you would see this picture this way. This is the glow that this guy has coming off of him because he has a temperature. You can see his hand through the bag. The bag is cold and his hand is hot. His glasses are cold, but his face is hot. And so you can see right through his glasses, but here they pop out because they're much colder. So they're not emitting the same kind of infrared radiation as his face because his face is hotter. All right? So the point is, hot things are emitting light. They're emitting radiation. So that's the first part. Now, If we want to ask what the temperature of the Earth should be and why it should have a certain temperature, we can say, all right, well look, here's the Earth. It's sitting there. It's getting light fed to it by the sun. And it's also emitting light. It's also emitting energy. It's absorbing energy, but it's also emitting energy. Now, why is that? Why do we know it's pretty obvious that it's absorbing light from the sun. But the reason why it's emitting energy is that if it didn't, it would keep gaining energy and gaining energy and getting hotter and hotter and hotter and just blow up. Right? It has to spit that energy back out, or else it would just keep building up and building up. So what's going on is there's basically an equilibrium going on. The power absorbed by the Earth is equal to the power radiated by the Earth. If that weren't true, then things would change. Okay? So that's an equilibrium state that the Earth has. The cool thing about this is it allows us to calculate the temperature of the Earth naively. If all of it we're doing was collecting light from the sun and glowing because it's collecting this energy. And I'm not going to work through the details on this, but I just want to show you that there's an equation. Don't even focus on it unless you're into this kind of thing. But the point is that we can calculate the temperature of the Earth knowing nothing but the temperature of the sun. Okay, that tells us how much light it's spitting out. The distance, the size of the sun, for example, turns out matters, and the distance we are from the sun. But given that we know all of these things, we can figure out the temperature of the Earth extremely precisely. The only minor thing we have to add is how much light's actually reflecting off the Earth compared to being absorbed by the Earth. More light is reflected if you have more clouds and ice and stuff like that. So that's a minor effect here, and that comes in like the fourth power of this fraction of stuff that's absorbed by the Earth. But the fundamental thing is we can calculate this. If you just treat the Earth like a ball of stuff, okay, like a naked ball of iron, it's getting light from the sun, you can calculate exactly what the equilibrium temperature of the Earth should be. Okay? And if you do this, lo and behold, you get an answer that's close, but wrong. You get a temperature that's 255 Kelvin, minus 18 degrees Celsius, roughly 0 degrees Fahrenheit. The naive expectation for the equilibrium temperature of the Earth at the surface of the Earth is 0 degrees Fahrenheit. Turns out this is wrong. And the reason why it's wrong is that this is the temperature of the surface of the Earth in the absence of any kind of blanket it might have. This is actually what the temperature of the edge of that blanket is. But if the surface of the Earth is engulfed in a blanket, it can be warmer. Okay? So let me walk you through this a little bit. But fundamentally, it has to do with, imagine the sun's like a campfire and you're a person, okay? And you're some distance from the campfire. And you're so far away from the campfire, you're still kind of cold. If you put a coat on, you might be comfortable as a distance from that campfire. The coat is like our atmosphere. So why is the Earth so warm? Okay, why is it not frozen? Because you can do this calculation very basically. It's because we're forgetting about our coat. We're forgetting about the fact we have this atmospheric blanket. And this is where we get to talk about the greenhouse effect. The greenhouse effect is an interesting thing, and how it works is like this, and maybe you've heard this before, but it's called the greenhouse effect for a reason, okay? A greenhouse is hot. Why is it hot inside a greenhouse? You might think, well, look, the light from the sun is coming into the greenhouse. But the heat inside that greenhouse is not getting back out those same windows that the light is getting in, okay? So there's light coming through the windows, and then when stuff inside the the greenhouse gets hot, it starts emitting infrared radiation. That's what heat is. But that heat does not escape the windows. So while the visible light comes through the windows of the greenhouse, the infrared light, which is the heat, doesn't escape the windows of the greenhouse, and so it can get hot. And greenhouses are great because they let all the light from the sun in. So they're letting all that light in, which is getting you hotter and hotter and hotter, but they're not letting any of the heat out. So it just bakes in there. So the greenhouse effect on Earth is sort of the same thing. There are particular molecules. Okay, fundamentally what happens is the visible light from the sun makes it all the way to the Earth. It heats the Earth. Okay, the Earth gets hot, it emits infrared radiation back out, but that a lot of that infrared radiation is subsequently absorbed by certain types of gases in the atmosphere called greenhouse gases. And then those things re-radiate energy back towards Earth and back up into space. That's basically how a blanket works, okay? You are emitting heat, okay? You put a blanket on, that traps some of that heat and bounces it back to you, and you sort of keep yourself warm. But it's your clothes and your blankets that are allowing that to happen. Okay? Except rather than a normal blanket, this would be like a see-through blanket that lets all of the energy from the sun in to hit your skin, but then traps that heat on the way back out. Are there questions about this? Okay. The three most important greenhouse gases in the atmosphere are carbon dioxide, methane, and water vapor. These molecules are particularly interactive with infrared light. They absorb infrared light very readily. So they absorb that heat very readily, and that's what allows them to act as this effective blanket. Now, here's what the Earth's atmosphere is made of, and here it is by percentage: nitrogen, oxygen, then we have water vapor, argon, carbon dioxide. The first two things, nitrogen and oxygen, are not effective greenhouse gases at all. That infrared radiation goes right on through them. They don't act like a greenhouse. Water vapor does, and you're very familiar with this, right? When it's humid, it feels hotter, right? You're familiar with this. We're in a place with not much humidity, and so you're like, what are you talking about humidity? But I imagine at some point in your life, you've been somewhere where it's kind of humid, it can feel hotter, right? Now, the second most important greenhouse gas is carbon dioxide. Now, you may have heard a lot in the news about carbon dioxide as a greenhouse gas and a lot less discussion of water vapor as a greenhouse gas. That's because water vapor is not continuously in the atmosphere. A molecule of water will get released into the atmosphere, you know, after it rains or from water or something, but it will only stay in the atmosphere for about a day or a few days. And in fact, that's why the water vapor content on Earth varies so much. It doesn't get mixed up. So there's not a constant water vapor fraction in the atmosphere. It depends on where you are. So some places are humid, some places are very dry, and there's not enough time for that water vapor to get spread all over the atmosphere. So it doesn't act like a global thing. It doesn't build up in the atmosphere. Carbon dioxide, on the other hand, can last a very, very long time in the atmosphere. In fact, carbon dioxide molecules can last greater than 1,000 years in the atmosphere. Some people have estimated that it's 100,000 years or even 1,000,000 years in the atmosphere, depending on the process to get that carbon dioxide back out. So what means is you put carbon dioxide in the atmosphere, it stays there for human terms, effectively forever, most of the time. The main way carbon dioxide is scrubbed out of the atmosphere in short term is via plants. Plants basically eat carbon dioxide. Okay, so plants do absorb carbon dioxide, but if you put more carbon dioxide in the atmosphere than plants and oceans can absorb, then it just builds up. There's no good mechanism to get it out. Methane is also an important greenhouse gas, too. This is a complicated diagram you can stare at a little bit if you want to, but I don't want to get into that. Now, I showed you this basic equation before. The cool thing is we can apply it to any planet. It wasn't specific about the Earth. So we know what the sun's temperature is. We know how far other planets are from the sun. We can then calculate equilibrium temperatures of all the planets and ask, what do they look like compared to this calculation? And if we do that, this is what we get. Here's the naive calculated temperature in the absence of the greenhouse effect. For the Earth, Mars, and Venus. The Earth ought to be minus 18 degrees Celsius. Mars ought to be minus 56 degrees Celsius. And Venus ought to be minus 39 degrees Celsius. Now, you might look at this and say, well, the Earth is wrong. Mars is pretty good. Venus is just way the hell off. Like, this isn't even close. What is going on? Okay. Now, Mars, it turns out, as we've discussed earlier, has almost no atmosphere. That's why you get the answer right. So the greenhouse effect on Mars is only 3 degrees, whereas the greenhouse effect on Earth adds about 33 degrees. The greenhouse effect on Venus adds 466 degrees. In fact, the atmosphere of Venus is incredibly thick, incredibly heavy, and it's all carbon dioxide. And that's why it has this crazy greenhouse effect. We think that something on Venus, we think something called the runaway greenhouse effect has taken over. That has just built up carbon dioxide in the atmosphere of Venus and made it hotter and hotter and hotter. We will return to this later because we think in the very beginning, Venus and the Earth were actually not very different things, but they've had catastrophically different histories. Okay? Venus, 96% carbon dioxide, a very heavy atmosphere. Mars, 95% carbon dioxide atmosphere, it turns out, but it's very, very thin, and so it doesn't really do that much. And the Earth is only 0.04% carbon dioxide. So the amount of carbon dioxide in our atmosphere is very small, very, very small, but it plays a really, really important role in setting the temperature of the Earth. Why so little carbon dioxide, you might wonder? Given that this thing's a lot like us, this thing's a lot like us, what happened to the carbon dioxide on Earth? Well, we think, in fact, the Earth was born with a very rich carbon dioxide atmosphere. Volcanic gases, in fact, that we think were very important in creating the initial atmosphere of the Earth are very, very rich in carbon dioxide. It turns out that the kind of stuff you see coming out of volcanoes, you guys have seen there's this erupting volcano happening right now in Chile. I was actually going to put a movie of it, but I didn't have time. But it's got, if you were to study the stuff coming out of that thing, it's a lot of carbon dioxide, nitrogen, water vapor, and sulfur dioxide, but basically a lot of carbon dioxide, and that stuff was really important in driving the initial atmosphere of the Earth. All expelled from these primordial volcanoes and things. However, the primordial carbon dioxide, although it started out 1,000 times more carbon dioxide than we have right now, it eventually got scrubbed out of the atmosphere. And it got scrubbed out of the atmosphere because we have liquid water. Okay? H2O, it turns out, can rain out of the atmosphere. It creates a mild acid out of the carbon dioxide. It can absorb in raindrops and water vapor and fall down to Earth. Okay? So this carbon dioxide can then dissolve in water, like oceans and rainwater, and fall out. And then once it's in the water, once it's in the oceans, it can precipitate out and eventually create create limestone. Eventually it gets incorporated into limestone deposits at the bottom of the oceans. And then the nitrogen too, that made up the next bit of the original atmosphere, stayed up there. So all that nitrogen is probably primordial, whereas all that original carbon dioxide that made up our atmosphere, it's all locked in limestone and stuff like that on the Earth today. So most of the carbon dioxide on the Earth is locked up in crustal rocks and dissolved into the oceans. So it's all basically fallen out, and it's all sort of locked into the Earth and deep underwater. Here's an example of limestone. A lot of that carbon dioxide has been incorporated into stuff like this. Now, there is a carbon dioxide cycle that operates on the Earth that acts as basically a thermostat. That's been very important in shaping the temperature of the Earth and keeping the temperature of the Earth actually pretty stable over time. And I want to talk a little bit about that now. When I talk about geological timescales, I'm talking about millions and millions of years, hundreds of millions of years in some cases, to hundreds of thousands, so very long timescales. So what happens is, you put a lot of carbon dioxide in the atmosphere, it makes the Earth warmer because it's a greenhouse gas. But when the Earth heats up, it rains more. And that scrubs carbon dioxide out of the atmosphere. And so there's a cycle where if it gets too hot, carbon dioxide is just flushed out of the atmosphere, and so then it cools down again because the greenhouse effect goes down. Yeah?
So we need more global warming to get rain in California?
No. So what's happening right now with the short-term greenhouse effect is very different. And I'll talk a bit about that. I'll talk a bit about that sort of at the end. But the sort of short timescale issues that we're dealing with right now are very different than these. But broadly speaking, when it gets hot over a long period of time, there's more evaporated water from the oceans, and then that water can then fall back down. But the local drought that we're having right now is very complicated and has to do with like climate patterns on the Earth versus other places. There are, of course, other places on Earth that are experiencing unprecedented monsoons, unprecedented rainstorms and flooding, right? So I'm talking about average over the globe and not these local problems that we're having. It's a complicated issue. Now, once this carbon dioxide is flushed out of the atmosphere by rains, okay, it gets into the oceans, etc., precipitates out and forms limestone, which makes the bottom of the oceans. Now it gets incorporated into basically the plates, and then those plates subduct other plates because of tectonic activity, and effectively that carbon is re-released via volcanism back up into the atmosphere. So over very, very long periods of time, carbon dioxide that was up in the atmosphere falls out and then gets pumped back up via volcanoes. Now again, I'm reminding you, this is very, very long periods of time. We're not talking about 100 years here, right? We're talking about hundreds of thousands of millions of years that it takes to take some carbon dioxide that was once in the atmosphere, put it down into rocks, have that stuff subduct, and then vent back out via volcanism, right? This is a very long period of time. This is geologic timescales, but over those timescales, there is a regulation. Okay. So, what happens then, you can imagine though, again, over very, very long timescales, imagine the Earth gets cooler for whatever reason, okay? The sun goes through a periodic cycle where it starts spitting out less energy, the Earth cools down. The Earth cools down, that means there's less evaporation from the water, from the oceans, and therefore, in the long term, less precipitation all over the Earth. Because there's less precipitation, less carbon dioxide is being drenched out of the atmosphere, and so carbon dioxide builds up over time as volcanoes are spitting more and more carbon dioxide over time, right? It doesn't stop the volcanoes from adding the carbon dioxide, but what's happening is you rain less, so you don't scrub that carbon dioxide out. So it builds up, and after enough time, you build up enough carbon dioxide, the greenhouse effect sprouts, gets bigger, and the Earth warms up. Okay? So it acts as a thermostat. The heat comes on, right, when it gets too cold. Vice versa, if it gets too warm, there's more evaporation, more precipitation, more carbon dioxide scrubbed out of the atmosphere, the greenhouse effect goes down, and it cools down. Okay? So this Earth, carbon dioxide cycle acts like a thermostat. And so over a very long period of time, it keeps the Earth's temperature range pretty stable against big forcing events. Okay. Now, something that I emphasize is that this acts over 100,000 years to 10 million years timescales. So it takes a long time for the thermostat to kick in. Okay. So what we're experiencing right now, for example, is this increased temperature that we've seen happening over the last 50 years. Okay. We've cranked the thermostat up, okay, and we want that carbon dioxide to start being scrubbed out of the atmosphere by rain, but it's probably going to take 100,000 years for that natural cycle to kick in. Okay, that doesn't help. The Earth's cool with that. The Earth's like, I got this, whatever. I'm 4.5 billion years old. This is nothing. But us, that's like our species here. That's a long time. So this is why people are freaked out about carbon dioxide levels in the atmosphere. Okay. Now, this balance, okay, this balance that drives the carbon dioxide cycle can, in principle, get thrown out of whack or get forced by other things that affect the temperature of the Earth. For example, how much solar energy we're getting. The tilt of the Earth, it turns out, is wobbling a little bit over time. The orbit of the Earth is subtly changing over time, and those things can affect the source term, the amount of energy we're receiving from the sun, and then affect things. Asteroid impacts can kick dust up into the atmosphere, which reflects more light from the sun, which effectively, therefore there's less energy delivered to the surface of the Earth, and things will cool down, right? So there are external forcing factors that can change things that affect the climate of the Earth that cannot, in short term at least, be regulated by the carbon dioxide cycle. And of course, the human activity that's putting all this carbon dioxide in the atmosphere is also something that's happening on such a short time frame that the Earth can't respond. let me just take a poll here, and I'm not going to judge anybody. I'm just interested in this. Raise your hand if you believe that global warming or climate change, but broadly speaking, it's global warming, is influenced by human activity. Okay. If you don't believe that, I'm wondering too. Raise your hand if you don't believe that it is. What if you're not sure? Some people have not raised their hand. It makes me very confused. Okay, but most of you are convinced by this. Not everybody is convinced that human activity is playing a role in global warming. And one of the things you can do in a science class like this is try to do something quantitative that's simple to ask yourself whether or not you think it's reasonable to believe this. Okay? Now, climate modeling is very complicated. It's extremely complicated. And the experts are doing their best on it. But as sort of people who can do math, do rough math, we can ask ourselves, do we think that this is a reasonable thing? Okay, so let's do a simple exercise to get a sense of the issue. The greenhouse gases that are important in the atmosphere are water vapor, carbon dioxide, and methane. Okay? Water vapor, I've already talked about, varies a lot. But the carbon dioxide is something that's reasonably stable, and it makes up about 0.04% of the atmosphere. And it turns out that if you given what we know about greenhouse gases, this corresponds to about 20% of the greenhouse effect on Earth. The majority of the greenhouse effect on Earth has to do with this water vapor that we're very familiar with. Okay, but this is something that varies and jumps around. This is something that stays in the atmosphere for a long time. So approximately 20% of the 33 degrees that bump we get because of the greenhouse effect comes about because of carbon dioxide. So that's 6 degrees. Okay, that's a non-trivial amount. 6 degrees. Now, how much mass are we talking about in carbon dioxide? Well, you take 0.04% of the mass of the atmosphere. Mass of the atmosphere is 5 × 10 to the 18 kilograms, and this fraction is 0.004. You multiply those two numbers together, and you get 2 × 10 to the 15 kilograms of carbon dioxide that's in the atmosphere of the Earth. That's a big number, okay? It seems like a lot. The Earth is big. That's a lot of carbon dioxide. Let's ask how much by a fossil fuel emission alone, okay, there's other sources of carbon dioxide that we're putting in, but just from fossil fuel burning alone, how much carbon dioxide are we putting out in the atmosphere per year? It's about 10 to the 13 kilograms a year. Okay, now, that's not that much different than all of the carbon dioxide in the atmosphere, period. Okay? So this total CO2 content of the whole atmosphere will be expelled in 200 years. You'll double it. You'll double the second most important greenhouse gas. And remember, I'm telling you that it stays in the atmosphere for thousands of years. So had this number been 100 times smaller, you might have said, well, I don't know, it would take 20,000 years for us to get to the point where we're even doubling it. And by that time, we won't be using carbon dioxide, we'll be doing some other source of energy. But this makes you a little bit nervous. So just on that sort of back of the envelope calculation, it seems reasonable, okay? So that's one thing I just want to leave you with. Another thing that seems pretty obvious is that the carbon dioxide content of the atmosphere is going up like crazy. This is an observatory in Mauna Lea in Hawaii that's been measuring the CO2 concentration of the atmosphere up there since the 1960s. And this is how the carbon dioxide parts per million in the atmosphere has been changing over the last sort of 50 years. Now, notice the little wiggles. Those little wiggles are wintertime and summertime. Okay? In the summertime, all the plants come alive. They gobble up a lot of carbon dioxide because that's what they eat. And the carbon dioxide drops. In the wintertime, those plants die and release their carbon dioxide back up in the atmosphere. So over year-to-year timescales, the carbon dioxide content of the atmosphere changes in response to that biosphere. But on top of that yearly wiggle is this regular rise. You can also look at global temperatures of the land. You can do this on ocean too. This is how the global temperature of the Earth has changed since 1960 when the measurements started. It's been doing this. The coldest year in the past 135 years was in 1909. the warmest year on record so far is 2014. So it's about a degree warmer than the coldest, and of course there's yearly fluctuations. There's always yearly fluctuations. This is particularly interesting because the sun went through a solar minimum right around here. Okay? The power output from the sun was actually at a minimum in the 2000s between this era here, and yet at that time, while the temperature kind of flattened out, it didn't go down as you naively would have expected it would have. So we think that the origin of this flattening actually has to do with the sun. The sun got colder. Not colder, but less luminous, basically. Now you can go back 2000, back to the year 1000, measuring the carbon dioxide in the atmosphere from ice cores. It was pretty level at this point up to about the time of the Industrial Revolution, and then starts shooting up. This is the temperature variation on Earth over that period of time. And you see that, again, right around the same time, it starts shooting up. It's kind of naively what you would expect to happen as you increase greenhouse gases. This goes back 400,000 years. Okay? Again, from ice cores. And there's this periodicity, interestingly, in the carbon dioxide fraction of the atmosphere that's sort of embedded on sort of 100,000-year timescales. But here we are. Okay? And since this point, for 650,000 years, the atmospheric carbon dioxide has never been above this line, and now it's here. So it seems pretty evident that, we know we're putting carbon dioxide in the atmosphere. We know it takes thousands of years for the carbon dioxide to get scrubbed out of the atmosphere on average, and we measure it higher than it's ever been. Now, let's go back in time, though, these geological time scales. See these dips? It turns out that these periods of time where we see these dips are associated with periods of great glaciation of ice ages. And in fact, this is a period of time going back 540 million years. You see the temperature on Earth has fluctuated into these periods when it's been very cold, and during these cold periods, the Earth has been basically covered in ice. Those temperatures correlate very much with the carbon dioxide in the atmosphere, as you would expect. Okay, I'll tell you what. This is a good time to stop. I will pick up here talking about global ice ages in our next lecture, and nothing from this point on will be on the midterm. Okay, so we'll stop at the greenhouse effect on Earth. I won't do global ice ages and stuff like that on the midterm. All right, thanks.